Good evening to all. My name is Ganesh Shankar Bhandari, and I am a PMRF PhD research scholar in IIT Roorkee, and I am here to take the live session for week 8 for the NPTEL course Principles of Extractive Metallurgy, taught by Professor Tarun Kumar Kundu. So we will start with the previous week lectures revision. Then based on the previous week lectures, we will try to solve some MCQ problems, which will further help you to solve your assignment problems uh, for the for the particular course. So first we will start with the previous week lectures revision. So until now we have learned about the mineral processing like beneficiation processes, liberation sizes, how to grind them or how to crush them, different types of crushing processes, grinding processes. Then followed by we had learned about various roasting processes which are helpful during the pyrometallurgical processes of the non-ferrous metallurgy and ferrous metallurgy. Then we had learned about different types of furnaces used in the pyrometallurgical operations. Then different types of refractories used in the in the furnaces for creating high temperature environment. Then now in this week lectures we will talk about the process. In this week lecture, we will talk about the extraction of copper, which is a very important, we can say very important non-ferrous metal. So the important non-ferrous generally includes the copper, zinc, and lead metallurgy. Then we can learn about the nickel also. So now we will talk about the copper extraction via flash smelting process. So yeah. So last few decades. Normally, in the 1920s or 1930s, they were producing the copper with the help of the reverberating type of roasting furnaces. They were going for the matte smelting process. They were going for the matte smelting process. Then after matte smelting, they were going for the conversion process to produce the blister copper, and then blister copper was subjected to the electro refining processes to get 99% purity copper metal. So with the enhancement in the with the technological enhancements and new research going on, now they have shifted towards the flash smelting process for the copper production. So the last few decades, new and improved methods of copper production have been evolved in order to realize they have to increase the productivity because nowadays we can see the demands for the copper metal is going increasing and increasing because in every electronic items whichever we are using in our day-to-day life that requires enormous amount of copper metal inside them. Without the copper metal we cannot imagine our day-to-day life because cannot uh, we cannot produce the electronic items without the help of the copper metal. So we need for fulfilling this increasing demand of copper metal, we need to increase the productivity of copper via mining processes. Then we have to evolve the process in order to improve the demand in order to meet that demand increased demand for copper production. So in a few methods and improvements have been done in the copper production, like they have increased the productivity, then lower specific energy consumption, increase environmental protection and sustainability, then increase reliable operation, control and safety. And these developments has lead to the decrease in the number of processing steps. Like earlier, first we were going for oxidation roasting process, then matte smelting, then converting, then electromechanical processes. Now, with the help of the newer processes, these processes can be done in a single furnace at a time. Previously, they were doing it in the different furnaces, in, including different steps. So we can decrease the number of process steps, then continuous processes over batch processes, then autogeneous operations. use of oxygen or oxygen enriched air, then tendency towards electrometallurgical methods, increase energy concentration per unit of volume, electronic automation, measurement and control, then recovery of sulfur and waste heat. So nowadays they are also recovering the sulfur gas produced during the copper pyrometallurgical processes in the form of H2SO4 acid, which can be further used during the hydrometallurgical processing of the copper metal. Then they are also regenerating the waste heat, or we can say repurposing the waste heat generated during the whole operations. Then they are recovering the valuable byproducts, like they are recovering H2SO4 acid, sulfur gas in the form of H2SO4 acid. They are trying to recover the precious metals from the anode sludge of the copper during produced during the electrometallurgical processing. Then uh, pro- they are trying to extract different metals present inside that copper ore as an impurities. Then new trends in copper metal smelting processes. So when we talk about the copper pyrometallurgical process, so then we talk about copper metal smelting processes generally, because copper generally found in the form of CuFeS2 as a in the form of chalcopyrite as a copper ore, and due to the presence of this sulfide presence inside this copper ore, we cannot directly go for the carbothermal reduction processes. So first we have to convert this copper sulfide into the copper oxide with the help of the oxidation roasting process, or we have to go for the copper matte smelting processes to, so that we can remove the iron present inside this copper chalcopyrite ore in slag material, because it will add on the impurities during the uh, copper production process. So total oxidation of sulfide ores with subsequent reduction to metal, avoiding the formation of copper matte, are used rarely due to its higher fuel consumption. So we generally don't go for the total dead oxidation roasting process. We generally go with the oxidation roasting process just to convert the FeS2 present inside this CuFeS2 ore in the form of FeO material, so that it can report to the slag form. So copper-rich slag formation and crude copper production with high impurities level, we have to do it. Then prior to 1960s, the most important way of producing copper was partial roasting sulfide concentrates, then smelting the calcine in reverberative furnaces and converting the matte in Pierce-Smith converter. So then molten flash smelting and subsequent converting has become predominant pyrometallurgical copper extraction methods in nowadays, and as flash smelting is the most efficient and economical process which can reduce the costing up to 35% compared to the conventional reverberatory furnace process. This is because smelting is the largest energy consuming step, and flash smelting is autogeneous due to combination of exothermic roasting and endothermic smelting process. So we can control the heat inside the furnace, and with the help of that heat control, we can reduce the cost for the fuel. We can reduce the cost of the fuel used during the furnace itself. Then the hydrometallurgical processing depends on the copper content, but generally the capital costs are 50% lower than conventional processing. Sometimes we also go with the hydrometallurgical process for the copper production. Like if the copper ore is having very lower grade, like 0.2 or 0.1%, or if it is in the form of the oxide ore, then we generally go for the hydrometallurgical copper operations. Then coming to autogeneous smelting process, autogeneous smelting involves the use of roasting heat generated by fast reactions of the sulfide concentrate in suspension. So during the during the oxidation roasting process, as we all know, this the oxidation roasting process is an exothermic reaction. So during the autogeneous smelting process, we are utilizing that exothermic heat generated during the oxidation roasting process for the smelting of the copper matte. Then spatial and temporal coupling of exothermic and endothermic reactions leads to an economical process, but the sensible heat of nitrogen in the air causes a deficit in the heat balance. Thus, measure taken for preheating combustion air with waste heat or in a preheater. So we are providing preheated combustion air inside the furnace for the oxidation roasting process. then we are trying to increase the oxygen content of the combustion air. Like if we are just going with the air, so it will contain only 21% oxygen. But that is generally that is required for the oxidation roasting process, which is going to help to generate the temperature inside the furnace via exothermic oxidation roasting process. So we are trying to researchers are or companies are trying to increase the oxygen content in the air pulse during the processing step. Then combustion of natural gas, fuel oil, or pulverized coal in supplementary burners, so that we can provide the proper heat inside the furnace, then removal of moisture in the concentrate by drying it before the charging process. Because if it is content 4 to 5% moisture also, then it will also reduce the energy efficiency during the whole process. We have to provide more and more energy inside the furnace for the removal of that uh, moisture content. Then minimization of flux addition as far as practical to save energy. Then autogeneous smelting processes have several advantages like high rate of reaction or increase in the production rate. Then it is helping in the energy saving process, and it is using the exothermic. It is also using it is combining the exothermic reaction and endothermic reaction during the processing steps. Then low volume of off gas and high SO2 content, which can be easily converted to the H2SO4 acid. Then low quantity of flue dust if oxygen is used. Then there are some disadvantages like high copper content of the slag. The slag generated during this autogenous process will contain the high copper content. So we are going to lose some copper metal inside the slag phase, which needs to be recovered from that slag phase via separate processing. And then autogenous smelting, there are various autogenous smelting methods which are generally which the companies are using nowadays for the production of copper metal. One is autocompu flash smelting process, which is developed by an Japanese company. Then Inco flash smelting, then Kipset cyclone smelting, then flame cyclone smelting process. So coming to the Autocompu flash smelting processes, large unit comprises three sections. Like it is a continuous process for the copper production. So we are talking about uh, oxidation roasting, then smelting, then converting of the copper inside the same furnace. So first one is this furnace consists of three sections. One is circular reaction shaft, which is generally 6 to 7 meter in diameter and 7 to 9 meter high. For roasting, we generally use for roasting and smelting dried concentrate in suspension. It is generally producing the copper matte. Then settling hard for collecting the molten droplets and separating matte from slag. Then after the matte production in the circular reaction shaft, we are going for the conversion process. Then there is rectangular uptake shaft for waste gas and flue dust discharge processing. The waste gases are separated from the flue dust at around 1250 degrees Celsius in the offtake shaft and pass through a waste heat boiler for generating steam, and subsequently to an electrostatic precipitator for separating the flue dust, which is recycled to the feed. So we are also recycling the heat energy lost during lost with these flue dust with the help of the regenerators. Then after that, we are going with the electrostatic precipitation process for separating the flue dust from before releasing the flue gases in the environment. So autoclave flash smelting operation, generally we use a concentrate which is having less than 10% moisture, and flux are mixed and dried in rotary or flash dryers. The dried feed is conveyed to the top of the reaction shaft. So generally we go with the Yeah. So this reaction shaft is the reaction shaft which is having 6 to 7 meter high in the autocomplete flash smelting furnace. It is generally used for the oxidation roasting process, and oxygen enriched combustion air which is created up to 500 degrees Celsius is introduced inside the conventional burners and used for additional firing. The heterogeneous mixture of gas particle droplets remains in the reaction shaft only a few seconds before reaching the settler, which contains a liquid matter containing 50 to 70% of copper and slag around containing around 2% copper. which is separated at around 1200 degrees Celsius in the hearth region of the furnace, and the matte is tapped for the converting process. So then froth flotation and reduction in small circular electric slag furnaces are used for slag cleaning process. So 4CuFeS2 with the help of the oxidation roasting process is getting converted into matte, which is containing copper sulfide and iron sulfide plus iron oxide, which is going to get reported inside the slag phase with the help of the reaction with SiO2 as a flux material. So there are some new trends which have been included in these auto compo flash smelters nowadays, like increasing oxygen content in the blast air, like Inco flash smelting, then production of blister copper from concentrate in single vessel, like continuous smelting and converting in Noranda process. Then there is Inco flash smelting process. So in the Inco flash smelting process, the construction is similar to that of the medium size river battery furnace, but feed and oxygen are blown horizontally through burners at both ends of the furnace. So, auto compo flash, when we were talking about the auto compo flash smelting process, it was like co-current process. From the bottom, the oxygen was going on, and from the top, we were feeding the material in the powder form so that it can get it can oxidize in the presence of the oxygen, which is having a temperature of around 500 to 600 degrees Celsius. In the Inco flash smelting process, we are going with a horizontal blow of oxygen through burners at both ends of the furnace. The offtake is arranged at the center of the roof. In the auto compo smelting process, the offtake was at the end point of the furnace. In the Inco flash smelting process, the offtake is at the it has the middle of the furnace. The offtake is aligned at the center of the roof. A sheet steel encasing keeps the furnace nearly gas tight. The advantage of the process rests on the use of pure oxygens, like relatively small gas volume containing 80% SO2, and it produces negligible dust formation, relatively low energy requirement, and the simple design because we are using pure oxygen in the burners, so it can help to reduce the heat losses via flue gases because there is no nitrogen presence, which is a major cause for the heat loss in the flue gases. Then advantage of Inco over autocompo processors. Inco process have lower energy requirement and 30% higher throughput because we are providing the pure oxygen inside the furnace. So it is creating more and more exothermic reactions during the processing itself. So we need lower energy requirement via fuel and via other fuels. And 30% higher throughput, same size furnace than autocompo process. Then Inco process have lower dust losses, lower volume of effluent gas because we are not providing the nitrogen. We are not using air for the oxidation roasting process. We are using pure oxygen for the uh, oxidation roasting process of effluent gas with higher and it due to the use of the pure oxygen for the oxidation roasting process, the resultant effluent gas will contain the higher amount of the SO2 content, which can be easily converted to the H2SO4 for producing a byproduct during the whole processing. Then coming to so at present, more than 32 Outokumpu furnaces are in operation with a total capacity of nearly one third of the world primary copper production. Inco process have lower energy requirement and 30% higher throughput than Outokumpu process as it is operated with pure oxygen. In the Outokumpu process, we are going with the air as a oxidation roasting source. While in Inco process, we are going with the pure oxygen for the oxidation roasting of the copper sulfide to convert into copper matte. Then, yeah. Then there is bath matte smelting process. So current copper matte smelting processes can be divided into three different processes like conventional, which generally use oxy-fuel laboratory furnace or electrical furnace. Then there is suspension smelting, from which we had already talked about the flash smelting process from in the auto compu furnace and flash smelting process in the Inco furnace. Then there is cyclone type suspension smelting process, which can be divided into flame process and kipset process. Then there is bath smelting, um, also known as matte smelting and conversion process, which can be further divided into different furnaces, or we can say different processings, different processes developed in the different parts of world. One is top submerged lance processes, which include osmelt, isasmelt, serosmelt, and which are these processes has been developed by the Commonwealth Scientific and Industrial Research Organization, Australia. Then top jetting lance, in this process, the Japan has developed a Mitsubishi process. Then Tuer process includes Noranda, Bain, Tank converter process. Then Vancouver processes. Then bottom blowing smelting processes are there. So there are different types of processes which is generally used for the pyrometallurgical production, for the production of the copper metal via pyrometallurgical operations. So the extraction of copper from CuFeS ores by pyrometallurgy includes we are starting with the sulfide ores, which is having a copper concentrate from 0. In the range of 0.5 to 2.0% copper. Uh, while talking about, if we talk about Indian copper grade, then we generally have a grade of around zero point 0.7 to 0.8% copper with in the form of chalcopyrite ore or copper ore. Then first steps is comminution process. Then after comminution, we generally go with the froth. Companies generally go with the froth flotation steps to concentrate the copper from this zero point 0.5 grade to increase the grade to 20 to 30% copper. Then this 20 to 30% copper grade is So this 20 to 30% grade can directly we can directly go with the partial roasting. We can go with partial roasting processes followed by matte smelting, or we can go with the drying process followed by flash smelting or matte smelting process, or we can go with the dry smelting process and multi-furnace continuous copper making followed by the for producing blister copper, or we can directly go for the direct to copper smelt with this 20 to 30% copper for direct copper smelting process to produce blister copper. So depending on the process, what type of process we are trying to adopt, the process steps can get changed. Like first includes partial roasting followed by flash smelting or matte smelting to produce blister copper. Then second one is drying followed by flash smelting and converting to produce the blister copper. Then coming to the KIPSAT cyclone smelting process, the acronym KIPSAT uses the initial letters of the Russian terms, which includes oxygen, vortex, cyclone, electro, and thermic. The continuously operated method is aimed at processing copper sulfide concentrate that contains considerable amounts of other metals. The essential part of the plant is the smelting cyclone, in which the concentrates are fed vertically and technical grade oxygen having 95% purity is blown in horizontal, so that reaction takes place rapidly above 1500 degrees Celsius. So what is happening here? We are feeding the copper sulfide ore into a cyclone, and with the counter current from counter current process, we are producing the oxygen in the counter current direction, and it is getting reacted with the copper ore to get them converted into for the in the oxidation roasting process. The furnace is divided to allow separating and settling of the reaction products, similar to a reverberatory furnace, but the electrically heated settler is maintained in a reducing atmosphere so that the slag does not need special post-treatment processes. The off-gas volume is small with high SO2 content, as we are already going with the high purity oxygen. So it will the off-gas will largely contain the SO2 gas, which can be easily converted to the H2SO4 as a in the byproduct formation. Metals are recovered from the flue dust of both the separating chambers and the settlers. Then coming to flame cyclone smelting process, the principle of this method differs from KIPSAT process is that the reaction in the FCR process takes place in a special chamber situated before the cyclone, where the molten droplets are separated by centrifugal forces. Then volatile compounds of other elements such as zinc, cadmium, tin, lead, arsenic, antimony, and bismuth, which are generally present as an impurity material in the copper ore. as oxides and basic salts are simultaneously removed in the fluidus part, and that fluidus can be further recycled to recover these elements according to the economical processes. The SO2 content of the off gas is generally higher than 50% because we are using air with some high amount of oxygen high amount of pure oxygen. Then autogenous high temperature can be created inside the furnace more than 1500 degrees Celsius. Roasting and smelting of copper sulfide concentrate occur in a high oxygen atmosphere. Like we are providing the high oxygen purity up to 75% in the air. Then high grade matte can be produced containing 80% copper and slag separates in a settler. It is well suited for processing complex or lean concentrates. Then there is a numerical problem. So we can see the chalcopyrite copper concentrate is given, which is containing CuFeS2, FeS2, and SiO2, containing the mass balance is given 20%. It is containing 20% copper, 36% iron, and 41% around silica, and rest sulfur, and rest is silica, which is smelted in a flash smelter to produce matte with 50% copper grade, where remaining S is oxidized to SO2 by passing theoretical amount of air. So we are providing theoretical amount of air to produce SO2 content. The flux is silica, assume pure, and the slag contains 70.588% FeO and rest is SiO2. So find for 1 ton 1000 kg concentrate amount of matte produced, amount of slag produced, amount of flux required, amount of the off gases generated, amount of air supplied, fall of matte, composition of slag. So in these types of problems, we generally go with the mass balancing process. So whatever the input we are going to provide, input is going to be equal to the output. So input what we are providing the concentrate as a input material. Then we are providing the oxygen gas as a input material. We are providing SiO2 as a flux material. So that are going to be our input material. What will be the output material? One will be the matte. Then there will be slag production. Then there will be there will be off gases. So the atomic weight and all things are given. So now going with the mass balancing process. So first we will try to mass balance the copper material. So copper is coming from concentrate and it is going to the matte, and it is going some part of copper is also going sometimes it can go with the slag also. However, here it is given that slag is containing 75%, 70.58% FeO, and rest will be the SiO2 content only. So copper will not get reported into the slag phase. It is coming from the concentrate and it is going to get reported into the 100% copper is going to report in the matte phase. So copper in concentrate as CuFeS2 we can calculate. Then Fe in concentrate we can calculate. So the amount for the amount of matte produced we are it is given that it is containing 50% copper grade. Okay. Where remaining S is oxidized to S2. So, according to that theory, 50% copper grade, we can calculate the amount of the matte. So, copper in matte will be 2000 kg, 3.15 kg per mole, Cu2s. So, copper matte, the copper will be present in the matte in the form of the Cu2s. Okay. So, with the help of that, we can calculate the amount of the matte produced because we have this 50% copper grade in the matte. Then amount of slag produced in the slag generally FeO and FiO2 is reporting inside the slag material. Then amount of flux required we can calculate according to the FeO dot SiO2 dot SiO2 reaction. Then amount of off gases generated we can calculate like off gases. In the off gases we can think about two things. One is SO2, then second one is N2. And here we are saying that we are just providing a theoretical amount of air so that whole so that all of the sulfur which is not going inside the matte is going to get converted into the SO2. Okay, so according to that reaction, we can calculate the theoretical amount of air required, but you have to keep in mind the nitrogen content inside the air, because air also contains 79% of nitrogen. Then amount of air required we can calculate for matte slag composition in mass percentage. We can because then we have already calculated the amount of slag produced, and with the help of Fe dot SiO2 content we can determine the composition of the slag material. Okay, then coming to the next yeah. So after matte smelting process, we have produced a matte which generally contains Cu2s and some other metal sulfides, like if nickel is present there, it can be in the form of nickel sulfide or some other metal sulfides, which are not uh, going to get oxidized during the matte smelting process, or we can say oxidizing roasting process, and has not reported to the slag phase. So converting reaction is the transformation of a molten metal sulfide, Cu2s or Ni3H2, into metal by the action of air or oxygen by the following mechanism. So we had already learned about the predominance area diagrams in the sulfide chemistry. So based on the predominance area diagram, we can determine the thermodynamic calculations for this conversion of metal sulfides to the respective metal oxides, and from metal oxides then it is going to get reacted with metal sulfide to produce the respective metals and SO2 as a flue gas. So converting takes place when the following conditions are fulfilled. The sulfide should be melted easily without volatilization, at which appreciable conversion rates can be achieved. Then the oxide form should be miscible in the molten sulfide, so that the metal sulfide and oxide reaction takes place rapidly. The metal form should be insoluble in the molten sulfide oxide phase, so that it forms a separate layer. Okay, so the major motive behind this converting process is to we want to separate the metal from these metal sulfides. So the metal form should be insoluble in the molten sulfides or oxide phase, so that it forms a separate layer. These conditions are only fulfilled for the Cu2s. Okay, remember, there are numerous numbers of elements are present inside this Cu2s concentrate in the form of impurities, like PBS is present there, nickel, some amount of nickel is there, some amount of gold and silver is there, some precious metals are there. However, as we already know, the precious metals does not get react with the sulfur or oxygen, so they are going to get reported in the metal phase only. However, the lead and nickel, which is present inside this Cu2s as an impurity material, these are not going to fulfill these conditions. Like PBS is volatile in nature. PB sulfide is volatile in nature, and at that particular temperature of around 1000 or 1200 degrees Celsius, it is going to get volatilized and not going to melt it readily. So it is going to get reported inside the flue gases. Then there is nickel oxide, which is insoluble in sulfide, and Ni is soluble in sulfide phase. Okay, so NiO and Ni has high melting point around 1600 degrees Celsius. So Ni most of the time is going to get reported inside the slag phase, or we can say the reaction is not going to properly happen during the converting process, due to the insolubility of nickel oxide in the sulfide phase, which in turn inhibit the reaction between the nickel oxide and nickel sulfides to produce a metallic nickel. However, on the other hand, nickel metal, which is going to produce during the reaction, is a soluble phase in sulfide phase. So it is not going to get report inside the metal content. So conversion of this copper matte is generally done in the Pierce-Smith converter. So copper converting in a converter takes place in two stages. One is slag making stage, then Second step is copper making stage. So in the during the slag making stage, matte produced in the matte smelting furnace is intermittently mixed or charged with the silica flux into the converter, while air with or without oxygen enrichment is blown into it. And with the help of this oxygen enrichment, whatever the metals present, or we can say metal sulfides are present inside the copper matte, they are going to get converted into the metal oxides via oxidation roasting process, and with the help of the SiO2 they are going to get reacted with this SiO2 material. Generally, when we talk about the copper matte, so the major impurity is iron sulfide. So iron sulfide is going to get react with the oxygen getting converted into Fu, and this Fu is going to get reacted with the flux material which we have added in the form of SiO2 to form FeO.SiO2 and to form the slag material, and can be skimmed off, and a new batch of matte is charged inside the PLC Smith converter. This continues until all the FeS in the matte is oxidized, leaving a white metal which is majorly Cu2S, copper sulfide. Then during the copper making stage, this copper sulfide, we are going to further oxidize it to produce crude molten copper blister until all sulfur is getting oxidized in the form of SO2 gas. So the major reaction happening during this step is Cu2S is going to get converted into copper oxide and SO2. Then this copper oxide is again getting react with copper sulfides, as we had already talked about. Copper oxide, the metal oxide present should readily react with the copper with the metal sulfides to convert them into the respective metals. So copper fulfills that particular condition, and this Cu2 is going to get reacted with Cu2S to convert them into metallic copper and SO2 gas as a byproduct. Converting takes 2 to 3 hours to produce blister copper, which is having a purity of around 98% copper. And some impurities will be present inside this blister copper like nickel, cobalt, iron, tin, bismuth, arsenic, zinc, lead, and some precious metals like gold and silver will be also present inside this copper matte, or we can say copper blister. So further these impurities can be removed during the electro refining process of this copper to produce 99% grade, 99.9% grade copper. So these impurities are going to report inside the anode sludge during the electro refining process, and from that particular anode sludge, we can extract these precious metals one by one via different processing steps. Then converting technology, the industrial converting technologies can be grouped into bath smelting and suspension smelting process. So bath converting generally consists of tuer type bath converting. So the common example of tuer bath converting is Pierce Smith converter, which is the oldest one and is still the most widely used one. Then there is Noranda continuous converting process, Hoboken converter, which use injection into matter, then Vanuco process, then Bain process. Then there are top submerged lance, which is generally used for lancing the oxygen inside the converters. So there are some processes like Osas melt, Isas melt, Ceros melt, which has been developed by the CSIRO Australia. Then there is top jetting lance Mitsubishi process, which has been developed by the Japanese company. Then there is suspension converting like flash converting processes like Canocot Autodeck flash converting, which is the newest one, and use solidify matte powder as a feed to a flash furnace. Then there is Inco flash converting process. So coming to the Pierce is Smith and modified Pierce Smith converters, the most important conversion unit. Uh, it is a horizontal cylinder type structure having 9 to 11 meter height and 4.4 to 4.5 meter dia. Then lined with basic magnesite or chrome magnetite bricks that can be rotated about its long axis. Blast air is blown through a horizontal row of side blown tubes, punching of tubes with special devices necessary to maintain the flow of air. Then with a modification in this particular Pierce-Smith converter, they have produces some another, they have uh, designed some another converter process which are better than this Pierce-Smith converter like Hoboken or siphon converter. This variation of the PS type developed by metallurgical Hoboken NV Belgium with a small converter mouth and a siphon goose or neck that guides of gas and fluids. It is free from sucking in air, so the off gas can contain SO2 level up to 12%. Then there is Caleton's modified converter, which has been recently developed with two separated mouths for charging and off gas flow and a lateral tap holes for liquid slag and white metals. Then there is inspiration converter. Okay, so there are some converters. Okay, so now coming to the nickel sulfide conversion. As we had already talked about previously, the nickel sulfide is very difficult to get converted into the nickel metallic part during the copper copper pyrometallurgical process. And the major problem is that somehow we have to recover this nickel content from the copper ore during the copper converting or matte smelting process because we have very limited ores of limited source of nickel metal and with the help as we all know the demand for the nickel is going to increase manifold due to the use of the electric vehicles nowadays because these particular vehicles contains lithium metal oxide batteries and the nickel is a major content inside nickel uh, is a major content inside this lithium metal oxide batteries. So we need to find more and more nickel sources. So we cannot leave behind this nickel content. And as we already talked about, the nickel is very difficult to process during the metal smelting or converting process due to the miscibilities of the nickels due to the miscibility of nickel metal inside the nickel sulfide. So the conversion of nickel sulfide reaction with standard enthalpy like Ni3S2 plus 7O2, 7 by 2 O2 converting into NiO. Then this NiO is going to get reacted with Ni3S2 converting metallic nickel. Contrary to the production of blister copper by Cu2s or Cu2O interaction, nickel sulfide is not converted easily to nickel because the free energy change for the reaction is positive. As we can see, the delta G is 21 kilojoules. So why this is positive? Because it is having lower the nickel oxide produced during the this reaction is having lower miscibility inside the nickel sulfides. So, if there is no miscibility of nickel oxide and nickel sulfide, so it is very difficult to get them reacted to convert the nickel into metallic nickel. So, means have to be provided to mix NiO intimately which is having a melting point of around 1900 degrees Celsius in the sulfide phase to prevent its slagging and to have as a high temperature of around 1600 degrees Celsius to keep metallic nickel in the molten state. So, in order to keep the metallic state, in order to keep the nickel in metallic state, we have to increase the temperature during the process more than 1600 degrees Celsius. These were successfully achieved by Inco Metal Company by using a rotating converter provided with top-blown oxygen lamps and turbulent bath. When the sulfur content of the batch reaches around 2%, the O2 blowing is turned off and a neutral or slightly reducing flame is used to maintain 1650 to 1750 degrees Celsius in order to permit the residual oxygen and sulfur to react and produce nickel containing nickel which is containing less than 0.001% sulfur content. So generally this is CSIRO labs have developed a TBRC type reactor, which is known as top blown rotary converter for solving this nickel problem during the copper smelting process. So this converter is a short cylinder led horizontally or a slight inclination 18 degree from horizontal and rotate at slow speed around their axis. Oxygen is introduced by water-cooled lamps from the top opening. The combined action of O2 jet and rotation enhances the oxidation reaction in the molten bath. And this also used in steel making process like Caldo and rotor processes, and for Cu and Ni production. It operates at around 1650 degrees Celsius and produces around 50 tons pure nickel in 3 to 4 hours of batch processing. So NIO can react with the refractory lining to produce a variety of high melting silicates like high melting silicates, aluminates, spinels, and NIO MgO solid solution which physically interfere with the reduction process. And successful conversion of nickel sulfide requires strict control of the amount of NIO formed during the whole processing step. Despite extensive research conducted in 1950 to 1980 on the development of TBRC at the Noranda Research Center, the process failed to attain commercial status outside Canada. So TBRC is used batch-wise for special operations on a small scale like converting copper metal with high levels of bismuth and arsenic, then direct smelting of concentrate to white metal or blister copper, then slag treatment from sulfide concentrate smelting and native copper, copper extraction raw copper scrap and metal recovery from other secondary materials like electronic waste are also carried out in this particular TBRC furnace. So generally, the most followed flow sheet during the copper extraction process is like formulation of copper concentrate, then followed by flash smelting furnaces, then converter furnace, then anode furnace, anode casting wheel, then producing anode for the electro refining process, and after refining, they go for the refined copper. They produce refined copper, while the anode sludge is treated for the precious metal recovery like gold and other precious metal volumes from this anode sludge. While the conver- while the SO2 gas produced during the converting process is generally converted into the H2SO4 for the hydrometallurgical operations. Mm, So there are some other processes also. Okay, so now we will try to solve some some MCQ problems. So first MCQ is what is or are the advantages of the autogeneous smelting process used in the copper production? So it provides high rate of reaction by or increase, or we can say it increase the production rate. Yes, autogeneous process provides the high rate of reaction and increase the production rate because we are going with we are combining the exothermic reaction, which is generally the oxidation roasting process, and the endothermic reaction, which is generally smelting process at the same time in the same furnace. So the rate of reaction or production rate get increased during the whole processing. Low volume of off gases and high SO2 content, which helps in easy conversion to H2SO4. Yes, it produces low volume of off gases because we are we generally use 80% pure, at least 60 to 80% purity oxygen grade inside uh, these particular furnaces for oxidation roasting process, uh, which in turn results in the high content in the SO2, high content of SO2 in the flue gases because there is no nitrogen present, very lower amount of nitrogen present inside the gas pulsed inside the furnaces. Then low quantity of flue dust if oxygen is used. Yes, that is also true. So answer is all of the above. Which of them is an autogeneous smelting reactor? Autocompo flash smelting, yes. Then Inco flash smelting, yes. This is also autogeneous smelting reactor. Flame cyclone smelting, yes. So answer is all of the above. Match the following. Copper is so there are some copper smelting processes, and generally the furnaces used inside these particular copper smelting processes. First one is conventional. So during the conventional processes, we were using this oxy fuel reverberating furnace, which is which were in use until 1950 or 1960 in the major companies. However, now they have shifted towards the suspension smelting and bath smelting processes, which combines the um, smelting and converting processes at the same time and resulting in the uh, higher grade SO2 content in the flue gases by using the high grade oxygen used inside the furnace for the converting process. Then suspension smelting process is generally consist of autotake, flash smelting and inco process. Then bath smelting is Osmelt and SS melt, which has been this process has been developed by the CSIRO Australia. What are the conditions required for the converting process? So when we were talking about the converting process, we had talked about some particular conditions which needs to be fulfilled during for the converting process to happen. So the sulfide should be melted easily without volatilization. Yes. For example, Cu2s Cu2s sulfide complete this requirement, so we can go for the converting process. However, in the case of lead sulfide, it is not possible because lead sulfide can be easily volatilized at a temperature of around 1000 or 1200 degrees Celsius. So it is very difficult to convert the lead sulfide into particular lead metals. Then oxide form should be miscible in the molten sulfide. Yes, generally Cu2s formed Cu2O formed during the converting process is miscible in the molten sulfide so that it can get reacted with the copper sulfide. So Cu2O is going to get reacted with copper sulfide to convert the copper sulfide and copper oxide into respective copper metal. Then the metal form should be insoluble in the molten sulfide oxide phase. Yes, otherwise it is not going to we are not going to get a different layer of copper metal and copper sulfide during the whole processing, which is the major idea behind this particular process. Why is the conversion of PBS is not possible? So, as we had already talked about, conversion of PBS is not possible because PBS can get volatilized at particular temperature, which are generally 1000 to 1200 degrees Celsius during the smelting, during the conversion process. So, PBS is volatile and cannot be melted readily. So, due to this, so insoluble in metal phase and required high energy for the process. Nothing. Man, thing is PBS is volatile and cannot be melted readily. Then which of them is presented as impurity in the blister copper? So generally Ni is present as an impurity in the blister copper. Cobalt is there. While Si, it is going to get reacted with the Fe content and converting that iron oxide into FeO.SiO2 so that they can report into the slag phases. On the other hand, the Al is also going to get reported in the slag phase in the form of Al2O3.SiO2 or Al2O3.SiO2.CO if we are using limestone as a flux material to for the proper reaction or to decrease the viscosity of the slag formed during the pyrometallurgical operations. Then what is or are an advantages of the TSL process? Flexible fuel type, coal, oil and natural gas. Yes, that can be used in the TSL process. Then minimum feed preparation is required. Yes. Versatility in terms of running oxidizing and reducing conditions in the same furnace. Yes. So all of the above is true for the TSL process. What is our disadvantages of the Noranda process? So raw copper produce contains 1 to 2% sulfur, which needs to be removed in Pierce-Smith converter. No, this is not the advantages. Gases leaving this reactor contains low SO2, cannot be economically recovered, thus emitted to the atmosphere. Yes, this is the disadvantages of the Noranda process. Then amount of copper in the slag is appreciable and brings a heavy load for the recovery. Yes. So these two are the disadvantages of the Noranda process. Okay, so this is for today. So now we can